First of all, I apologize for anyone who was watching the live stream and has encountered some technical difficulties. Unfortunately, no idea what happened, but for some reason my drawing screen that I'm recording was lagging. I did some fixes. Hopefully it will work now without any hiccups. Let's make sure it works. Test 1 2 3. I mean, it looks good on the OBS screen. Hopefully it will look good once I export it. What I wanted today is to go back. I'm gonna divide this streaming session. I don't want to do any more domain specific streams. I'm gonna maybe stream for 2 hours, but I'm gonna do things that I'm interested in and things that are interested to me in order to fill up the slot. So what I wanted to do here is go back to the prompt engineering video of last week and continue from scratch, not from that scratch, but from a different scratch. So I have this link right here, which is www.promptingguide.ai, and also there's another link that I was learning this from. It's a GitHub project, awesome generative AI guide. Okay, so if you want to learn with me together, let's start this. So I think I have a lot of prompt engineering here. Where are you, pal? Where are you? Here you are. Prompts and prompt engineering. Prompt engineering is a relatively new discipline for developing and optimizing prompts to efficiently use language models for a wide variety of applications and research topics. Okay, as we already said, it's just another way of saying that we are prompting stuff. We are giving instructions to the model. And prompt engineering, oh, this was written by AI, it seems. Not gonna jump to conclusions, but it says here, prompt engineering is not just about designing and developing prompts. It encompasses a wide range of skills and techniques that are useful for interacting and developing with LLMs. Okay, so prompts are ways for model interactions. Prompt engineering is another thing, and it's a domain of knowledges and skills that are useful for interacting with LLMs. So it's the usual things here in this guide as well. It just tells how prompt engineering is trying to better understand the capabilities and limitations of LLMs. It's just research on LLMs in the end, it seems, but hands-on research, so to say. Okay. This is something that I haven't heard of and seems interesting. It's called, just a second, LLM settings. So we have some settings that configure how reliable the model is and how desirable are the responses the model generates. So one of those is, do I have space here? Hopefully I do. So one of them is temperature. So the lower the temperature, the more deterministic the results are, in the sense that the highest probable token is always picked. So it goes the way of least pushback. If we increase temperature, it leads to more randomness. which encourages more diverse or creative outputs. So we can have examples here. We can say that we want to reduce the temperature for certain for certain responses. For example, a lower one we need for historical facts, and a higher one for something that's more creative in a sense. And then we have top P, which is a sampling technique. Top P, which is a sampling technique where we control how deterministic the model is. So how does it work? Is it the same as the temperature? Okay, then we have max length. We manage the number of tokens of the model. The model generates by adjusting max length. Stop sequences, frequency penalty. These are all interesting concepts to me. Max length, frequency penalty. It applies a penalty on the next token proportional to how many times that token already appeared in the response and prompt. So this reduces repetition. Interesting. So these are all the settings. Okay, let me go down. Let me go down again. Let me start from scratch here. So we already mentioned, so the prompt contains instructions or questions or instructions, context, inputs, and examples. Context, inputs, and examples. So we can write, I don't know, wow, I just realized how thick this guide is. But okay, so if we prompt the sky is, so the sky is, the output will be blue. So the language model responds with a sequence of tokens that make sense given this context right here. We can improve this, for example, by saying complete this sentence, and then we add the sentence the sky is. Okay. So what do I have? I have prompt elements. So a prompt can contain any of the following elements: instruction, context, input data, and output indicator. So as I said, instruction, which is a specific task or instruction you want the model to perform. Context, which is just additional information that can guide the model to better responses. We have the input data here, the input or question that we are interested to find a response for, and output indicator the type or format of the output. Oh, okay, so the guide also gives us some tips to keep in mind when designing our prompts. One of the tips is to stay simple. You can start with simple questions and then based on the context and the responses, you can add more context and more information to it. And then you need to iterate your question multiple times until you get the desired result. If we have a big task that requires a lot of moving parts, then we divide this big task into the moving parts, and then we feed these simpler tasks into the model. So next thing, we have the instruction. So this is interesting. The instruction is basically a command for the model to do what you want. Find me this information, summarize this, write, explain this to me. And another important thing, again, that I found out only recently when I did this stream, was that it's best to divide the instruction and context with any form of symbol. So if we have here explain blah 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 blah, and then I want to give more context, I can add a couple of these hashes, and then below I can say the problem what first appeared blah 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 blah, something like that. Okay, we also need to be specific. We also need to be specific about the instruction and the task we want the model to perform. Okay, so enough details for the model to perform well. A good descriptive prompt, a good detail form, but we need to keep in mind that the prompt can get too long if not careful, and also don't include too many unnecessary details. Okay. Wait, maybe I can. Okay, be precise. What else do I do? Okay, these are the examples. Oh, now we have some examples of prompts in the book, in the guides here, sorry. So let me move here. Let me move here. By the way, explanation is just text summarization. I didn't know this. I mean, I knew this. It never was obvious to me. So an example of prompt is summarization. We can say here explain a concept X, and then we write answer, and the model will produce X is blah 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 blah. I also didn't know this. A is an explicit prompt format that we use in question answering. I didn't know this. So why did we use it here? We are telling the model that we want an answer expected further. Okay. Wow. They can also extract information. They can classify. Data. Okay, so we can, for example, information extraction. We can write multiple paragraphs. Let's see. This is one. This is another one. And here we can say, here we can mention, I don't know, the moon landing. And we continue. And then we ask the model, mention the what was the big revolutionary moment that was mentioned in the text, and the model will extract the moon landing from it. Okay, it can also answer questions. It can classify text. You can talk with it. Interesting. It can generate code. Nice. They can reason. And so on and so on. All right, there are some prompting techniques now. I'm gonna stop here. And I'm gonna do something else here. Wait. Let me move this out of the way. And let me open this machine learning project. I haven't been back to machine learning in a long time, but where I stopped, I'm gonna tell you where I stopped. I stopped here. No, not exercise solutions. Where are the exercises? I want exercises. Where are the exercises? Ah, so the exercises are in the book. Okay. It's a good thing that we have exercises. And I'm gonna do them. I just want to wait. I'm gonna copy and paste this. I'm gonna rename it to exercises. And can I, is it possible for me to delete everything about the solutions? Okay. How do I delete all of this? One. No, it doesn't work like this. Delete cell. How do I outline? No, it's not outline. Or maybe I can just copy this cell and delete everything. How can I delete? Okay, I delete. No, I didn't delete everything. Delete. Now I delete. And now I can paste all of these here. Nice. So I haven't done this in a long time. I have no idea what I'm gonna do now. But let's try to make sense out of it. So let me show this. Let me zoom a bit. I can't, but let me zoom a bit now. Exercise number 1. Try to build a classifier from the MNIST dataset that achieves over 97 accuracy on the test set. All right. I need a classifier for the MNIST set that achieves over 97% accuracy. Accuracy, okay. And then we have a hint. The K neighbors classifier works quite well for this task. K neighbors classifier. Okay. You just need to find good hyperparameter values. Try grid search and alright. To be completely honest, I need to start from the basics. I forgot all about this. So first of all, a classifier. Yeah, I'm so rusty. A classifier is a machine learning model that predicts a category for given input. All right. So I need to build a classifier that predicts a category for a given input. The MNIST dataset is the numerical dataset, and we need 97% accuracy. So accuracy would tell us how often our model made the correct prediction. And accuracy is actually the number, as I already did, of correct predictions over the number of total predictions. So if I had 10 guesses and 9 times I said that something is correct, it's 0.9, which is 90%. Now, why can accuracy be misleading? If my dataset consists of 95, if it consists of 95% not spam emails, our model can predict everything as not spam and still get 95% accuracy, right? So if I have 5 spam emails and 95 not spam emails, and if I'm looking for the correct values, so it's gonna be 95 over 100. Yeah, so it can get the same thing and still get the correct accuracy. Now, what is the k-neighbor classifier? So it's a machine learning model that classifies new data points based on the majority vote of its neighbors. So imagine you have a bunch of labeled data points plotted on a graph, and you get a new unlabeled point. So KNN looks at the K closest points to it. It counts how many of those neighbors belong to each class, and then it assigns the most common class among the K neighbors to the new point. Okay, so how is this working? So let's say I have a point A, and the class of A is a cat. Point B is also the cat, and let's say, I don't know, C is a dog and D is a dog. So if I classify a new point here, it's gonna look at these 2 points. It's gonna assume that you're talking about the cat. Okay, so let's try to solve this. Let's try to solve this. Okay. So we need to train a classifier on this dataset that achieves 97% accuracy using k neighbors classifier. And yeah, I forgot to tell you, the k neighbors classifier has two important hyperparameters: n neighbors, how many neighbors to look at, and weights, how to weight the neighbors. Okay, okay. Okay, let's remove all of this. Am I streaming? I think I am, right? I am. Can I run this? I need to find the environment. It's this one. Oh, it took 1.8 seconds, but okay. Let's load the dataset. I have no idea how this is done, so what I'm gonna do, I'm gonna look in this example here and see how. Oh god, I opened the wrong. Oh man, I made a mistake of the hook. I was supposed to open this one. Okay, where are the examples here? Here it is. Can I copy? Yeah, I can copy all of this. Copy cell, and I'm just gonna copy and paste this one, and I'm gonna call it O3 examples. And now I need to delete all of this, and I paste exercises. Okay. There are some tips here, but I'm not looking at this. I'm not looking at this at all. As a matter of fact, let me import a new field here. Nice. First things first. How do I import this data set? How do I import this data set? From this is how I do. I know that there are some 10x developers who can write this from their head and they know all the tricks. I have to copy code. But okay, fetch OpenML. MNISTE fetch OpenML MN. What's the wait what's the, it's like this. And now I can say we have X and Y. One is wait, let me first print MNIST. What's this one, brother? Oh no, are we gonna hit 10 seconds? Hopefully not. Hopefully not. Printed. So I have data and I have target, which are the two properties that I'm having here. So now I can pull X and Y, and one of them is gonna be MNIST data, and the other one MNIST target. Amazing. Let's split the data set. I'm gonna have X train. No, not this, brother. X train, and the X should be a big one because it's a matrix, and X test is gonna be X until 60,000, X from 60,000 to the end. Same thing for X. I'm just gonna use Y, and now I have X train and Y train. I'm gonna use this for training, and X test and Y test, and I'm gonna use this for testing. This is how a key-enabled classifier is called. I should also import it. And then I'm gonna fit it. To training data. And let's see the accuracy here. Come on. 9 seconds, 10 seconds. Come on, don't take this much. But the accuracy is 9.6. Okay, I'm just gonna copy this to the next cell. So I don't need to run all of this again. I could just do this. This one's also quite slow. Why is it slow like this? Wait, don't I have... Man, this should be fast. I have 64 gigabytes of memory. This should be lightning fast. Do I have 64 gigabytes? Yeah, here it says 64 gigabytes. Took half a minute. 9688. I'm not gonna look at this. Or maybe I should. So what should I do next? Let me open another coding cell. I need to create, first of all, the K-neighbor classifiers. Let me check. Where are you? It's here. Is it from Scikit? Yeah, it is neighbors. This implements the K nearest neighbors vote. Number of neighbors to use by default. We have some weights. Okay, what are the weights doing? Uniform or distance? uniform weights. All points in the neighborhood are weighted equally or distance. Weight points by the inverse of the distance. This case, closer neighbors of a query point will have a greater influence. Okay. Is there an example? Here it is. So what do I have? I import the classifier. I fit x and y. Then I predict 1.1. It's gonna be on 0. Nah. Okay, brother. So what I should do here is create a subject and neighbors. It's gonna be 3, 4, 5. And then I'm gonna have weights, uniform, and distance. And then grid search. Let me also import grid search as well. But wait, what is grid search doing? Okay, what is grid search? Grid search is the process of performing hyperparameter tuning in order to determine the optimal values for a given model. As mentioned above, the performance of a model significantly depends on the value of hyperparameters. But we have no idea what the best values are. Okay, how does it work? So these are the predefined values for hyperparameters. Now grid search tries all the combinations and evaluates the model for each combination using the cross-validation method. Okay. Okay, here am I continuing. So I'm importing what? Grid search CV. What am I taking as parameters? No man, lots of shit here. Estimator. What the fuck is an estimator? The estimator is my tneighbors classifier. Okay. What else? Paramgrid. I have those as well. Okay. What else? CV is gonna be 3. Scoring is gonna be accuracy. Verbose is gonna be 2. Number of jobs is gonna be -1. And then I want to fit this grid search fit x train y train trade. And then I'm gonna do this print best params. So what I'm doing here is I created the values to try in the combination. I created 3 cross-fold validations, which means that it's going to split the data into three parts. We evaluate this using accuracy. We use all cores to speed it up. My computer is, by the way, burning, so I hope this works. verbose, we give progress logs, and now if I click play, I have an error because this is not defined. Because in order for this to work, I should import it here. I don't want to run the cells above. Fitting 3 falls for each of 6 candidates, totaling 16 fits. Okay. An error again? Why? And the neighbors. What? Is it called the neighbors? Neighbors. Oh god. Ha, mistakes were made. So this is gonna take some time. Oh, it freezes, it freezes, it freezes, it freezes very hard. I'm using 8% of my CPUs. Let me close this. Yes, save, I don't care. Oh, it's gonna freeze. It froze. Oh no, did it? No, it didn't. Okay. I'm gonna close this. What else can I close here? Oh, I know a couple of things. This is running. I can turn you off. Maybe I can close you as well. Oh man, this is really slow. And my computer burning. I can basically feel it. Come on, come on, come on, come on. Come on, man. Oh god. Why does it take so long? Okay, while this is running, let's just explain what some of these mean. Do I have any logs here? No. So next I'm checking for the best parameters, and it will give us a result like, I don't know, n neighbors a certain value, weights a certain value. And then I'm gonna use the best estimator, and I'm gonna predict our predictions again using the best estimator. Okay, this needs to be quicker, brother. Come on, come on. You know what's the worst thing? Like TNN, it's really slow. So that slows it as well, especially when we divide it into 3 folds like we did here. It's gonna take quite some time. Oh man, it's printing something. So 6 minutes. Yeah, 6 minutes it took. So what do I have intended for these? So it needs 18 fits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Come on, 13, 14, 15, 16. Okay, baby, now when you finish this, you're gonna relax a bit. I'm gonna do some magic that you're gonna relax. Wow. Will it run 8 minutes? Man, I can only imagine how some of the more demanding data sets, how much time they take. Support vector machine, decision trees. There's a lot of things here. I think examples are really good because with examples you grow and you learn. 7 minutes. It needs 2 more, right? 2, 4, 2, 4, 6, 8, 10, 12, 14, 15, 16. Yeah, 2 more. Come on, brother. 2 more. 2 more. Come on. Nearest neighbors 4. Weights are distance of maybe of another code. Code cell. So what am I gonna do? I'm gonna do best KNN. It's gonna be grid search best estimator. So I'm gonna use best KNN predict test. Let's look at the score here. Score. This is gonna be y thread score. Wait. Fit predict. What's the difference between fit and predict? What's the type of this? This is the classifier. This is the classifier. This is an array. Will this work? This won't work. This won't work. Maybe it will. Of course this won't work, because this array has no best key and end. I can import the accuracy score. Okay, this was my bad. No, stop it. Accuracy score. Let's see. What? Can I print it at least? Print accuracy. Please don't. 0.9714, which means we hit the accuracy as we wanted it. Best score. Best params, best score. How did they estimate it? Grid search score. So they fitted it again. I should have done the same thing, but okay. Before the next chapter, I also want to build a spam classifier. I'm gonna build a spam classifier. What is this? Tackle the tonic dataset. Interesting. This is also very interesting, but I think the spam classifier will be really fun. Either the spam classifier or the tonic dataset. I'm gonna tackle one of them. How long have I been streaming? For 1 hour. At least 30 minutes more. So what I wanted to do now is the following. Let me close this. Let my computer rest for a while. Oh no. You know, I'm not gonna lie, I didn't expect the whole episode of today to end up being related to AI and machine learning, but I'm fine by it. So I'm just gonna go back to the basics now. Let us wait, let me just close some of these things I don't need, like you and you. Okay. So back to the basics. Let's go through some theory. Again, so what's machine learning? In relation to artificial intelligence. Again, Artificial intelligence is the set of all tasks in which a computer can make decisions. Computer, hopefully this isn't freezing, makes decisions. So anytime we look at a computer solving a problem by itself, diagnosing an illness, driving a car, categorizing images, giving you recommendations on Amazon, we are looking at artificial intelligence. So artificial intelligence is this whole field, which I drew already, if I'm not mistaken, but it's its whole field. This is all AI, and only inside we have machine learning, because machine learning is the set of all ways the computer can make decisions, but based on data. Which means that machine learning is part of artificial intelligence. So what's the difference between a human and a computer? And how people make decisions? They use facts, reasoning, logic, maybe even emotions, experience, and so on. Like when we want to buy a house, we look at the location of the house, and we did an example from the book at the location of the house, at the neighborhood, at the price, at the size of the house, at the current state of it, at the year it's built, at the amount of rooms, at the price as well. And maybe we can be emotionally connected to one possible house that we want to buy, but also experience. We can ask other people what they think. We can ask our friends, our family, people on the internet what they think about houses that have 3 bathrooms or houses that have a pool in front of the house. So in order to do this, we ask and we collect a lot of different informations from people, and these informations are actually data. And this is why ML is mostly related to data-driven reasoning, because we get the data and we make new predictions based on that data. Like, let's say we want to identify whether an image contains an apple, and how we know what an apple is. We learned what an apple is by knowledge, experience, and repetition. We know an apple has certain characteristics. We know an apple has a certain shape or even a certain color, and then we had to distinguish an apple from an orange or an apple from a pear. And that's how we learned. And we learned by repetition. We had to see many different apples, and we had to see some apples that were either green, others that were rotten. We had to see some that by green I meant they still weren't ripe, or some that were divided by color. They could be red or yellow or green. And basically the same thing how the computer does this is by repetition. We show the computer many images, and we can tell computer which image contains an apple. So then the computer can do this process until it catches the right patterns that make an apple. And then when it learns, it will use these patterns to determine whether the image contains an apple or not. And also, now look at this. We have AI, machine learning, and inside machine learning, we have also something called deep learning, which is the field of machine learning that uses objects called neural networks, which are, some say, implementations of human reasoning and human brains. And they have been used in, again, recognition, text generation, driving cars, movie recommendations, and stuff like that. Okay. Again, how human thinks in steps is that we learn from experience. We set a rule, and then we predict. So what does this mean? Based on our experience, let's predict, will it rain today? So from experience, we know that probably the last 7 days it rained every day. Okay, so we say, okay, is the rule for this that in this place it rains every day, and then we predict that because it rained every day, the rule is that it rains most of the days. So we predict that it's gonna rain today as well. Okay, now let me also get back to a couple of lingos that I forgot, like the always mentioned model. So what's a model? A model is an algorithm that represents the data we feed the model, and it's used to make predictions. Model is a simplified representation of reality, like the ones that we had with the California housing, in which we had all of these locations and all these extra parameters, which represent our, maybe not complete, but our version of reality. And in our version of reality, we have these lists of houses in these tables. And now we also have the algorithm, which is the process to build the model. Algorithm. So there's an example in this article. It says, okay, we have a friend and he likes to send us emails, but a lot of the emails that friends send us are spam emails. So we got an email from this friend and we want to guess whether it's spam or not without looking at it. And then based on these examples, on experience, rule, and prediction, we can say, okay, so based on experience, the last 7 out of 10 emails that our friends sent us were spam emails. So this is our model. And now we want to predict whether the next email is spam. So if 7 out of 10 emails our friend sends us are spam, then we can assume that the new email is 70% likely to be spam and 30 not to be spam. So we predict that the email is spam. Again, it might be wrong, but this is what we predicted with the best of our knowledge. Now, can we do this with a bit more with a bit more specificity? Let's say that based on certain days, our friends send us spam emails. For example, over the weekends, he always sends us spam emails. But during the week, he sends, I don't know, work-related emails. So we can even now create a new rule that says every email that our friend sends us during the week is not spam, and those sent during weekends are spam. So if today, based on this rule, we can make a new prediction. If it's weekend, Saturday or Sunday, we have a huge likelihood that this is some spam email. And if it's Monday to Friday, it's not spam. Interesting. But what if then our friend sees us one day and says, oh, I sent you a really important email in which I invited you to my birthday. You didn't come. Then you analyze the emails and then you see, he really did send me an invite, but because it was sent during the weekends, I thought it's spam. So we take another look at the data and we can divide this data now into sizes. And we can see that, for example, smaller emails that are only a couple of kilobytes big are regular emails, work-related emails, or emails that are not spam. And the bigger ones, because they have attachments and stuff, they are spam. So then we create a new rule based on all of this reasoning and based on all of this experience that we have. And what we did now is we have all these features. We have a property or characteristics of the data that the model can use to make predictions. So now what if we add more situations? What if we say during once a week you get a salary related email, which is really important. So what do we do now? How do we create models? How do we create rules? We can create rules saying, okay, if an email is larger than 10 kilobytes and it's sent on the weekend, so it's spam, otherwise it's not. But we can say if it's sent during the week because we forgot the birthday party, we need to check. So there's a lot of complexity that's being added as we add new rules and features. All right. How long is the stream going on? 1.5 hours. 1.5 hours. What else can I do today? I really had a AI related session, it seems. I really had a fun session. But what can I do apart from this? What else can I do? I know what else I can do. Let's talk about Unix a bit. Let's talk about Unix a bit. Let me open another one of these. Just a second. Okay, let's open the tablet again and let's talk about Unix now. Okay. So what's an operating system? An operating system is the software. So an OS is the software that controls the hardware resources of the computer and provide an environment under which programs can run. Generally, we call this software the kernel, since it's relatively small and resides at the core of the environment. Software that controls hardware, and the software is called the kernel. The interface to the kernel is a layer of software called the system calls. So we have the kernel in the middle, then we have the system calls right here. And then outside, I have applications. Okay, so when we log into Unix, we enter a login name. The system looks up our login name in the password file. The password file is usually etc password. So if we look at our entry in the password file, we see that it's composed of 7 colon separated fields. Okay, so what do we have? The login name, encrypted password, numeric user ID, numeric group ID, a comment field, home directory, it's home/name, and shell program. It's going to be bin ks shell. Okay. So what's a shell? A shell is a command line interpreter that reads user input and executes commands. The user input to a shell is normally from the terminal, an interactive shell, or sometimes from a file called a shell script. So a shell, it's just the terminal here. So what are the common shells that we could use? We could use born, which is /bin/sh, born again shell, C shell, corn shell, 10x shell, all right? I don't care. I don't care. So the Unix file system is a hierarchical arrangement of directories and file. Everything starts in the directory called root. Okay, this is simple. Simple as well. So what else do we have? Okay, all shells have three descriptors when a new program is run. You have the standard input, the standard output, and standard error. And the standard error. If we run, for example, the command ls, all three are connected to the terminal. And most shells provide a way to redirect any or all of these three descriptors to any file. For example, I can say ls, this command file.txt. So this will execute the ls command with its standard output redirected to a file named file ls. All right, guys, I'm gonna stop here. I'm already 1 hour 40 minutes and I wanna take a break. Thank you. Bye bye.